my recording. That's too bad. So let's see if I can get us back to where we were. All right, there we are. So displacement is change in, again, it's a delta. So delta x technically means the final position minus the initial position. I won't write this all out every time, but you should become accustomed to being able to do this substitution. It will come up this year, especially when we do the calculus portion of this. But all of this represents displacement. That's the symbology I wish to use. Any questions about it? Yep.
In the second one, what's the subscript? The velocity
It's
x.
a little zero
Oh, okay.
for not initial position. I'll be consistent with that. So, and folks, I'll be consistent with that the whole year. Whenever we're talking about an initial anything, it'll get a little zero next to it. So initial momentum, initial kinetic energy, initial work done, all these get a little zero next to it. All right? So these represent the 5 motion variables, and they make up the foundation for uniform accelerated motion, often referred to as Galileo's motion variables. Now, I want to start our conversation very clearly. This is a set of motion variables that only work and only in conditions where we're able to take these areas. So when we've talked about taking the area and slope, what we're deducing today is under the conditions where we can take these areas, meaning when our acceleration is a constant. The things we learned today can apply in all circumstances. So I want to make sure you understand we're going to develop something today, but it is all predicated on the idea that we're dealing with a uniform acceleration. That word uniform here means constant. So in your textbook, they call this uniform accelerated motion. They will develop a set of relationships that are all referred to as Galileo's motion relationships, but they're all predicated on the idea that the acceleration is a constant. If the acceleration changes, you can't apply these rules the same. So these rules only work when the acceleration is a constant. Now, you can have a condition where the acceleration changes. I stand on the gas pedal and I accelerate for a little bit, and then I suddenly switch to the brakes and slow down to 0. That's 2 different accelerations. They might both be uniform, but I can only operate on one of them at a time. So everything we're going to do for the next few minutes assumes that the acceleration is constant over the time interval. That's the assumption. Please, don't discard that so casually. In this class, I will be making every reasonable attempt to trick you on that regard. And you will make that mistake, especially when we start introducing accelerations that change. The rules of Galileo only work under uniform accelerated motion. They do not work outside of that. So anytime the acceleration is changing, you can't use any of those Galileo's rules of motion. But sometime in probably November or December, you're going to want to because it's easier and you remember how to do it. But they don't apply. So let's talk a little bit about your homework because it plays directly into what we're talking about here. Nobody should have struggled on the first one because we did it in class. And I'm not sure anybody really should have struggled on the second one because it's really similar to the first one. But is there anything on this page to which you'd like me to speak to so I can use it for our learning here? Meaning, is there one of these that you'd like me to go over? Yes, ma'am. Number 3? Okay, so when it says to consider the ball in the previous example, it's trying to clue you into something that you had from the previous example. And that is that the acceleration here has to be the same because the ramp was the same. You may or may not have been able to garner that, but that's what it was trying to clue you into. So when I look at this, I'm only going to be able to do the third problem if I have successfully done the second problem. So let's consider the second problem. It tells me that I start from rest and that I accelerate to 6 meters per second in 3 seconds. Start from rest, 6 meters per second in 3 seconds. There's the graph that kind of complements that information. Now, that's 0 meters per second, 6 meters per second, 3 seconds. That suggests that I've been given the initial velocity, the final velocity, the time interval, but not the acceleration nor the displacement. Good so far? Yep.
I thought when it said it was slowed from 6 to rest, it was really
Oh, I'm sorry. You're right. I didn't even see the word slowed. I just plowed right through that. Thank you. So we should probably get rid of that. Do better. Although I don't think you guys did bad. It's just like I did bad. So let's try and get rid of that line. Apparently I'm not going to be able to. There we go. Hi, line. So I guess this will look better then. And to facilitate that, I'm just going to erase that there and do that. There. All right. We should probably do what the problem says. Not the one I wanted to do, but the one that's actually there. I assume that you guys did area and slope here, and that shouldn't have been too tough. So area was 1/2 times 3 times 6. So 9 meters. And slope, 0 minus 6 divided by 3. So -2 meters per second per second. Not so bad? Any questions about those? Because we need those in the next part. So let's go down to the next part. So it says, consider the ball in the previous example. It rolls up the ramp at a speed of 6 meters per second instead. But instead of being caught at the top, it rolls back down until it's traveling 8 meters per second in the opposite direction. So in this example, we are going to have different information. I think I can still draw a graph here. But the object starts with a positive velocity because it says it's rolled up the ramp at 6 meters per second, and it's rolling back down at 8 meters per second. So, I don't know, did you draw a graph like that? That work for you guys? So it starts here at 6, and down here, -8. But that also suggests our initial velocity is positive 6 meters per second. Our final velocity, -8 meters per second. And we know it's the same ramp, so our acceleration is -2 meters per second squared, but we don't have the time interval this time. We have other information, but we don't have the time interval. Now, you have the slope, so I'm pretty confident that you could iterate your way to figure out the time. And some of you, that's what you did. Meaning, you worked out in your head that after the first second, the new velocity was 4. And after the next second, the velocity was 2. And after the third second, the velocity was 0. And you could do that all the way until you got to 8. So that's likely how many of you decided to do the problem. And then, once you found out where that threshold was, where this point was, you were probably able to find the two areas to get the total displacement. I don't want to do that. And you should be able to understand why here in a minute. So I want to do something a little different with all of you, and I want you to pay very close attention if you've never been in a course of physics before, because I'm only going to do this once. And once you've done it once, you should be able to use it over and over and over again. So I just want to put this aside for a minute. Displacement is the area under a trapezoid. Correct? But the two bases represent the two velocities. The velocity at the start of the interval and the velocity at the end of the interval. And moreover, the height represents the time. Acceleration is slope, which means it's the change in velocity divided by the change in the time. Velocity is plotted on the vertical axis, time is on the horizontal axis. But change in has specific meaning as well. So we could write this as v minus v naught over t. Okay so far? Now, the thing on the left isn't that interesting, but the thing on the right is a little more interesting to me. So what I would like to do is rewrite the one on the right by multiplying both sides by t. And now what I'd like to do is move v naught over to the other side by adding it to both sides. Algebraically the same, but this actually has more value to me than the other one for a number of reasons. First, you should see its clear relationship to what you already know about linear algebra. We plotted t on the horizontal axis. We plotted velocity on the vertical axis. So the slope of our line is the acceleration. And where it strikes the axis is our initial velocity or our intercept. You see all those relations, right? Also, the reason this is more valuable is because this represents an actual motion equation. And I mean this not as a Galileo motion equation for you guys who had AP1, but it's a motion equation. It is v as a function of t, telling me where the object is at moments in the future. It's a function equation. This one is not a function equation. A function equation takes initial parameters and tells you something about the future. This is an initial parameter. It's how fast it's going at the start of the interval. This is an initial parameter. It's the constant acceleration applied to the object. T can be any moment in the future. That's why this is a functional relationship. You'll notice this one is not a functional relationship. It requires knowledge of the future event before it can tell you how far the object's gone. Right? The future velocity has to be known in order to figure out the displacement. Do you guys see those okay? Now, with that all being said, for you guys who are novices and are new to this, consider what's been given to us. Our problem started with an initial velocity, a final velocity, and an acceleration, but never gave us the displacement or the time. Our initial velocity was 6, final velocity -8, and the acceleration -2. And I should put units in there, but what I want to do is recognize that I can drop these values in where they go in both of these relationships. Final velocity here is -8. Acceleration, -2. Initial velocity, 6. Displacement unknown, but initial velocity again, 6. Final velocity, -8. Time, well, unknown. You have a total of 5 variables and 2 relationships that each have 4 variables in them. Meaning you're going to be able to solve for the missing 2 variables because you have 2 relationships that encompass all the variables. In this first example, it looks like I can figure out the time from one of the relationships straight away. Do you guys see that all right? So I can solve for the time almost immediately. Subtract 6 from both sides, get -14, divide by -2, and t's got to equal 7. Once I have the 7, pretty sure I can get the displacement right from there. This is algebra. And this is an algebraic way of doing motion relationships. That works for question number 3. And it works for the rest of them too. So before I go on, does everybody see what we started with? So what I would like you to consider is that you have two motion relationships. You guys who are novices recognize that every uniform motion problem is going to begin with identifying the information that has been given to you from a list of 5 things. And then you will use these two relationships somehow to identify the missing pieces of information. So I'm going to go to page 2 real quick, and it doesn't really matter which one of these we grab. They're all the same. So, want to take the one in the middle? Or the one on the bottom? I don't care. They got progressively harder, so which one do you want to do? The bottom one?
Sure.
Now, I'll point out, again, these are all really the same. It doesn't mean they're easy for you, especially if your algebra has been uneven over the last couple years. You'll have to make accommodations that you might take longer to do these. It says, and I'm going to start, and I hope this is something you will begin to consider doing, that every one of these problems is likely going to advance these 5 things. You're going to need to be provided with 3 of them. It's the way math works. So, a mountain goat starts a rock slide and the rocks crash down the slope 100 meters. That sounds like a displacement. You don't have to guess. It's in meters. It's the only thing that's here that can be in meters. So the units should probably tell you. Starts a rock slide suggests that the initial velocity of the rocks was 0. You sometimes have to interpret. And the rocks reach the bottom in 5 seconds. There's only one thing here that's in seconds. Now, based on what I know, this is the information provided. Any questions about that? I'm going to skip the graph. I don't care about the graph. I know V equals AT plus V naught. I can count on that. In this case, V equals A times 5 plus 0. I also know delta x equals 1/2 V naught plus V times T. That's delta x equals 1/2 0 plus V times 5. I'm sorry, delta x is 100. Looks like I can figure out a solution to this, doesn't it? I think I can get the velocity from one of these relationships and use it in the other. Do you see that okay? This one's not so bad. So, 100 divided by 5 is 20 times 2 is 40, so good for you guys? And then not terrible? I don't like all this substitution, but it works. Money? It's the hard money. It's not as good. I don't want to belabor this too much because this is uniform accelerated motion. It's not that interesting, but some of you are already seeing a pattern here. First, there might be a more direct way to get some of these answers. And this is still not physics. This is just kinematics. So allow me to at least point you in the correct direction here. Do you notice how there are 5 motion variables, but this relationship only has 4 of them? It's missing one. Which one? And you see that there are 5 motion variables. This one's missing one too. So this one has all but delta x in it. This one has everything but a in it. It's possible to create other relationships here. That's what we just did on this side. On this side, we solved for v in one relationship and plugged it into the other. So let's do that again. I'm going to take all of this and put it in here, but not with numbers. I'm going to create a new relationship that eliminates final velocity between these two. Algebra. I now have a new relationship that has 4 motion variables in it, but not final velocity. I mean, it's horrible though, it's ugly. We should combine like terms and expand. So, I combined like terms and expanded. My algebra's right. Make sure yours is. You'll notice that I'm kind of building something here. Off to the left is the variable that is not in the relationship. In the middle is a new relationship. 4 motion variables are there, but I eliminated velocity. In my prior example, instead of having to solve for one and then get the other, I could go right to the solution. If I wanted the acceleration and I didn't have final velocity, then it seems to me I could start with this relationship. Plug in all the things that were given. And I have a one-step solution to get the acceleration. Not solving for one and plugging into the other. You know that there's got to be 2 more of these, right? There has to be. And you should figure them out. If I want to find one that has V naught eliminated, then solve this one for V naught and substitute it. If I want one where time has been eliminated, then maybe solve this for time and substitute it. It will produce Galileo's motion equations. They are nothing exceptional. They are simply the results of uniform accelerated motion. You can also just look them up. They're also in your book. They're also on posters all over the school because lots of teachers make posters of the 5 motion equations. I will require that you commit them to memory. Let me make that very clear. I will require that they get committed to memory. And I'll probably require it by middle of next week. And that will mean that sometime next week you will have to recall all 5 from memory perfectly. Now, I would encourage you to come in tomorrow with all of them here. My expectation is at minimum you could look them up. But if you are new to physics, you should figure them out. All right. Kind of take us back to last week a bit. And I want you to look at these two graphs for just a moment and see if you couldn't tell me the displacement for both of them. I'm going to pick on one or two of you here, but you remember how we talked about finding displacement, and you guys are pretty sharp. So figure out the displacement in both of these real quick. That should be long enough to figure them both out. So I should be able to select two of you, and you should be able to tell me. But I'm afraid that some of you are hoping that you're not the ones to be selected, because I didn't see many people actually do anything. So either you've got it in your head, or you're hoping not to be called on. So make sure you have something in front of you that looks like an answer. I did not give this point, and if you're attempting to figure out where that point is, you're doing this wrong. Okay? I know you can figure it out, but I don't want you to. These are both trapezoids. And your equation for a trapezoid should serve you just fine. If you don't believe me, try it. This is a trapezoid where one of the bases is 0. No big deal. We've already seen that one. It's a triangle. This is still a trapezoid, even though one of the bases is negative. It's not a Euclidean trapezoid. It's a non-Euclidean trapezoid. That doesn't mean that it's not a trapezoid. It's what you would get if your trapezoid was a sunshade and you folded it. It still would produce the same area using the same relationships. Did you do 1/2 times the sum of the bases here times the time? I hope so. I mean, I know you could have just done a triangle, but you can still do 1/2 times the sum of the bases times the time. One of the bases is negative, but it still will work out just fine. And to prove it to you, you know that this is 2 seconds. Find the two partial areas and prove that it works out to be the same thing. Make sure you see that it's true. We can't go on today unless you can be convinced of this. Are you convinced and I can go on, or do you not know what I'm talking about? Because if you're not convinced, we can't move on. You all good? I hope so. It'll make later harder, and if you're unwilling to speak up now in front of 20 people, then how do you think you're going to do this in front of 200 in college? So I'm free to move forward. Yes, ma'am.
So you said that that's the trapezoid, like folded.
Mhm.
What do you mean by that?
I don't have a sunshade here. I wish I did, because my analogy would work great. But if you were to take like an ordinary piece of cloth like this and fold it that, like a sunshade would fold, this line becomes the crease of the fabric that folded down in front of you. I say this like a sunshade has been folded because what has actually happened is we've created an occlusion in the middle of our device. You would never call this, when you were in like 8th grade or wherever you had geometry, you would never have called this a trapezoid, right? Because it's got a point in the middle. You'd say it's 2 triangles, but never a trapezoid. But it fits the definition almost perfectly of a trapezoid. By definition, a trapezoid is 2 parallel lines and then 2 other lines. So I still have my parallel lines here and here. And I still have my other 2 lines here and here. Now, a quadrilateral can't be formed in this way because you can't have the 2 lines cross in Euclidean geometry. But in non-Euclidean geometry, you can. This still fits the definition of a non-Euclidean trapezoid. But it also means that you had to be in negative space for it to work, which is why it does. It works this way because the negative number has meaning here, and it wouldn't have, you would never have a negative side length in regular geometry, right? You never could do that before. But in non-Euclid geometry, you can. So it's still considered a trapezoid, which is why we can use the equation for a trapezoid to figure out the displacement. Now, this does not really tell us the whole area. You do realize that too, correct? This one might be harder. So let me just stop to make sure everybody's doing this right. What distance was traveled? You can't get that from the trapezoid formula. You can only get displacement. So I'm going to call on somebody for this one. You might want to check and verify with the person next to you the answer to this question. What is the distance traveled? All right, Ella, what is the distance traveled?
9.5 meters.
How did you get 9.5 meters?
I found the absolute value of the areas into the triangles and put them together.
So this area was,
2.
and we know it's negative, but you found the absolute value. And this area is,
7.5 meters.
how big is this one?
7. Oh wait.
3
Oh wait. Never mind. That's what I okay.
So 4.5 meters?
Yeah.
Okay, so Ella might have made a bit of an arithmetic error here, but do you guys see where those two areas come from? So the total distance traveled is 6.5 meters. But one of the areas is negative and one is positive, so the total displacement still works out to be 2.5. 4.5 plus negative 2 is 2.5. So we can use the displacement formula, but we have to understand that it only provides displacement. It doesn't tell us how far the object traveled. And it's not the individual areas. If you want the distance traveled, you will still have to compute it this way. How far did it go in the negative direction, and then how far did it go in the positive direction? So there are limits to what this can do. But the thing about using the trapezoid formula here is it provides a displacement across any time interval, regardless of whether the object was moving forwards or backwards. You do see that it successfully told us that the total displacement was 2.5 meters, even though the object moved backwards first and then forwards afterwards. But for the whole time interval, we got the full displacement without having to worry about what the object was doing. That's going to be critical for us moving forwards here. So we all on the same page, okay? It's a lot to take in, especially for a Monday. Before I go on, we need to cover something else that I did not cover last week, and it's probably about time I do. We have begun to use a lot of vocabulary. So for the next few minutes, I want to talk about the symbology that goes with that vocabulary so that we are kind of all together on the same page. Below these two graphs, I've kind of put together the symbology I wish to use. Get this out of the way. Maybe not. Go away. It's not going to go away. I'm going to have you guys just look down there. Hopefully you can see it well enough. So, there. These 5 symbols represent specific pieces of information that we need to discuss. And it leaves out several things that we've discussed this year already. But these are the symbols I wish to use for this year. There are 5 specific motion variables that we're going to be utilizing today and you were utilizing last week. And these symbols correspond to them. Starting with the bottom right, this is going to be time. More importantly, it represents the time interval. I should be writing this as delta t. but I don't. I just write it as t. But the shrewd ones among you who know what the delta means understand why it should be delta t. And for those of you who don't know, let's handle that too, because I know that there's students here who don't know what the delta symbol means. The delta is a Greek letter, so it's triangle. But as Greek letter goes, it means change in. When placed in front of any variable, it is the change in that variable. So putting a delta in front of a t means I'm looking at the change in time, or the time interval. It also means final minus initial. So when placed in front of a variable, we're talking about the final variable minus the initial variable. That is change in. You likely used delta when you did delta y divided by delta x way back in algebra. And that might be the last time it showed up. Maybe in chemistry. But get used to seeing delta in this class. We'll talk about the change in a bunch of variables. So the delta symbol gets used a lot. I just don't use it in front of time, even though I probably should. In a couple of days, we will talk about a similar symbol, which is a lowercase d, sometimes written like that, and sometimes written like this. These three d's are also representations of delta, but they are for a different discussion. They're for calculus discussion. So although we will come back to this, we will move our delta to a d when we start dealing with calculus. But it has a specific meaning as well. So be aware of delta, be prepared to use it, and understand that if you just put the words change in front of your variable, that's the meaning I want you to have. Now, we talked about acceleration last week, so I'm going to use a lowercase a with a bar on top of it. Bars on top of variables represent vectors. So when we put a bar on top of a variable, we are trying to tell you that your answer has to take direction into account. It also means that when you're asked about that variable, you had better take direction into account before using it. So for us, one dimension, that direction is positive or negative. But be prepared to talk about two dimensions here in about 3 weeks. These two v's represent initial and final velocity. You probably come from a training where they put a v with a little I or a v with a little f. I'm not doing that in this class. I will use a small 0 as a subscript to indicate the initial of any variable. It really means v when time equals 0. But we just write it as v with a little 0 next to it. They mean the same thing. But rather than write it as a functional notation, we just put the little 0 there. This is called a naught, N-A-U-G-H-T, like you're being naughty. So I will just say v naught, and you should know that that means the initial velocity. Yes, sir? I'm sorry, you're going to have to speak up.
Is the bottom one the first column, is that a V? Because it's hard.
This is supposed to be a v, yes. A v with a bar on top. Velocities are vectors, so they should also get the bar on top to indicate that they are vector quantities. And although I'm going to try and be consistent, I will forget to put the bars on top of the variables when we have equations and such. But when I list them out, I almost always remember, so you will hopefully be clued into to looking for that information when we start like trying to discern it from a problem. The last one is displacement. I will always write displacement as a delta x. It should have a bar on it too. It is a vector. But unlike delta t, I like to write the delta notation here because the truth is delta x does mean change in position. And we will have to write change in position out from time to time. Meaning we have to take into account that there is an initial position and a final position. So delta x has specific meaning, and substituting in this specific meaning will become important, especially when we add the calculus into this. So please be prepared to express delta x in its more raw form as x minus x naught. These are often called the Galilean motion variables. And they make up the foundation of uniform accelerated motion. Now, I want to be, pretty open with all of you guys. People tend to latch on to uniform accelerated motion and assume that that's the only thing we study in here. We do not. In AP Physics 1, you only study uniform accelerated motion. In here, we don't. We study motion that doesn't have to be uniform, uniformly accelerated. Meaning, what we're talking about today and for the next 3 days assumes that the acceleration is constant. Everything we have done so far has made that assumption that the acceleration is constant. To kind of exaggerate that some, remember, in our graphs from before, the velocities have always been changing at a constant way, which means your velocity graphs were either flat or straight lines. That's how you were able to use the definition of slope to figure out the acceleration. We assumed that the acceleration was constant. For the same reason, we were able to use the equation of a trapezoid. We can only use a trapezoid if what we had was two parallel lines cut by two other lines. That assumed the acceleration is constant. You cannot apply what we're going to talk about today in cases where the acceleration is not constant. So you need to ask yourself at the start of any motion problem, is my object experiencing uniform accelerated motion? Is the acceleration a constant? Now, you can have more than one acceleration in a problem, but you can only handle one acceleration at a time using this information. Now, I want to ask you guys, how hard were these? Number one should have been no trouble. Number two, probably no trouble. Did you start to have trouble with number three? Is that where the trouble began? And did that carry on and have trouble with number 4 and 5 and all that? Do you guys understand that number 3 requires that you had the acceleration from number 2? So, for those of you who didn't try this at all, sorry, you were expected to. And you're expected to kind of let me know how much of it you could do. I'm expecting that most of you got to the first page. But I had to text something out because people were sending me messages suggesting they were flipping out on it. 30 minutes was the most you should have spent on this. After that, no matter where you were, you should have given up and been done. Turned it in. So, do I have to do the second one? Or can one of you guys tell me the second one? I think you guys should be able to tell me the answers to the second one. So, it asked me for the acceleration and the displacement. Before that, I think you should be able to tell me other information that must have been given before we get to the acceleration and the displacement. All right. So Alexander, what was the initial and final velocity here?
The initial was 6 meters per second, and the final was 0.
Excellent. Excellent. So, let's see, we got not enough name tags, but Madeline, what was the time interval?
3 seconds.
3 seconds. So, Jada, can you tell me either one of the other pieces of information that's here, that's being requested of us? I'm sorry, Jana?
Sorry, what was the
So-
question?
Can you give me either the acceleration or the displacement?
The acceleration, I got -2 meters per second squared.
You got that from the slope?
Yes.
All right. And let's see, who can tell me the displacement then? Yes, sir? Divich?
Under 9 meters.
What's that?
9 meters.
9 meters? And you got that from the area?
Yeah.
So, anybody have a problem with any of these? Would anybody like them to be performed for you? Okay, so We go on to the next question, which is where things start to get a little more challenging. We're told it's the same ramp. I want to start by recognizing that them telling us it's the same ramp means that the acceleration here has to be -2 meters per second. Same ramp means that it's going to accelerate the same way. It's the angle of the ramp that makes that happen. We're told that the initial velocity is still 6, but now the final velocity is -8. It comes back towards you, so that means negative. We don't have the time and we don't have the displacement. This is what we're being expected to figure out. So, I want you to recognize that you have information at your disposal now. We know that displacement is the area of a trapezoid. And we know that acceleration is the slope. That's kind of what we've been given. You guys are more capable now. You might be able to do more things. For example, start at 6, end at 8. That suggests that the line looks something like this. You good with that? It also suggests that this was base 1, this is base 2. Is it clear to you that base 1 and base 2 are the initial and final velocities? If it's not clear to you, make it clear now. Because that's what they were. That's what they always have been. It should also be clear that the height is actually the time. Now, the acceleration isn't as hard for us to kind of extrapolate. It's got to be the final velocity minus the initial velocity. That is change in velocity over the time interval. Now, before I pursue this problem, I would like to change this. I don't like it, but there's something that I do like that can come from this. I want to multiply both sides by t. Then I want to add the initial velocity to both sides. Now, I'm kind of purposeful in why I want it written this way. This is actually a real motion equation. It tells us a future event based on a set of initial conditions. So it is a functional relationship, meaning it provides the function for the velocity in terms of the time by telling you where or how fast the object is going at all future times based on 2 initial parameters. Motion equations are special because they predict what happens to future events. And once you gain a little bit of calculus, you'll understand that having one motion equation means you have them all. So developing a motion equation is important. This is not a motion equation. Many people confuse it thinking it is, but it's not. Even though your textbook says it's one of Galileo's motion equations, it's not really a motion equation. And the reason is simple. It tells you the displacement of the object only if you know something about its future motion. Meaning it's not a set of initial conditions that predict future events. So this one's not a true motion equation and can't be treated as such. It cannot, by using calculus, tell us other features of the object's motion. It only works in this one instance because the area under the curve was a trapezoid. It's fortunate for us, but its flexibility is not very good. Now that being said, you have two relationships. For every one of these problems, you've had two relationships. And you have a collection of given information and a collection of unknowns. If you translate these two relationships into the information you've been given, you'll find things like, well, delta x equals 1/2 initial velocity, 6, plus final velocity, -8, times t, which is unknown. Can't do very much with this relationship. There's two unknowns in it. So I can't solve for either one of them. But in my other relationship, I have the final velocity is -8 equals a, which we know is -2, times t, which is unknown, plus 6. This relationship leads me directly to a path for the time. And once I have the time, I can figure out the displacement. I don't have to draw the areas. I don't have to perform on a graph. I can use these relationships, the definition of slope and the definition of area, to complete the process. So looking here, it looks like time is 7 seconds, right? And once I have that 7 seconds, it looks pretty easy for me to figure out what the displacement is. Good so far? So that's going to radically change what you do in page 2, isn't it? Pick one, I don't care. Yeah.
The question was asking for distance. So should we?
If it asks for distance, you're going to have to do more.
Okay.
If it asks for distance, you will have to figure out the partial areas. Let's circle back to that. Because still, I think we can get around having to graph it. Okay? But I want to apply what we just did to one of these, and I don't care which one. You guys pick which one. They're all about the same level of difficulty. You want the last one with the mountain goat? Yes, ma'am. Second one, fine. So, it says a ball is thrown upward, leaving the ground at 40 meters per second. There's an acceleration of 10 meters per second squared from gravity. How high does the ball go, and how long till the ball comes to rest? So, you throw the ball upwards at 40 meters per second. Let's begin to construct a resource of the information provided. One of the things that you will always see me do with uniform accelerated motion questions is to identify the information that is given. You guys who are sharp recognize that the two equations we have each have 4 pieces of information in them. You guys who may be seeing this for the first time, please notice that these two relationships have 4 pieces of information in them. That means you have to be given 3 pieces of information or else you can't solve a problem. We are told that the initial velocity of the ball was 40 meters per second and that it was positive, thrown upwards. I'm going to make upwards positive. This part's important. These are all vectors. They tell me that the acceleration is 10 meters per second squared. But if the ball was thrown upwards and I made that positive, I have to make this one negative. Gravity pulls things downwards. So if upwards is positive, downwards has to be negative. The bars above the top of your variables are a reminder to you guys that you must consider direction. For the time being, we're doing one-dimensional problems, so a positive or negative is all you have to consider, but you must consider it. Now, it would seem like we don't have any more information, but we have one more piece of information. The object makes it to its maximum height when the velocity is 0. That might not be obvious to you. You might have to reason that out. But if it still had velocity, then it's not at its maximum. And if it's on its way down, then it's not at the top anymore. That instant it stops, that's when it's at its maximum height. So that's 3 pieces of information. I'm pretty sure now this became the same problem as before, isn't it? I can plug everything into this one, figure out the time. And then once I've done that, I can use that to figure out the displacement. But I don't want you to do that. Folks, it should be clear to you that there might be a more direct way to do this. And for those of you who understand where I'm about to go, you should be able to do this already. If you can't, I would practice over the next evening. For you guys who are new to physics, I want you to consider that we are faced with the same problem we just did. I would like to be able to make these go a little more efficiently. What we did before was solve for time, and then use that to get displacement. If we do this once, we could do it for all problems as opposed to having to do 2 substitutions every time we're asked to do this problem. You should know what I've just done. I have solved for t and plugged it into the other relationship to eliminate t. Now, this isn't particularly pretty. So, oh, and this is a plus sign, sorry. But I do notice that I could factor out the 1 over 2a, and this becomes v plus v naught times v minus v naught. And you know what that is, don't you? You've seen that before. That's the difference of squares. So I would probably write this as and if you want my opinion, to make this easy to remember, I would multiply both sides by 2a. You understand that you could eliminate each of the variables in this way and create a new relationship. There are a total of 5 relationships. You should come tomorrow with all 5 of them. I've done the hard one. The other ones, the algebra is easier. Try it.